Okay, should we start? I am going to start with the doubt sheets. Okay, I guess this goes to the initial motivation. Maybe I should open that folder. Yesterday when we were talking about preconditioned CG, we came up with, where is it gone? Yeah. Is A hat symmetric, positive, definite? We can clearly see that it is positive definite. Question is, why is this symmetric? Why is Z transpose A hat Z a symmetric, sorry, why is A hat a symmetric matrix? If I want to test what is the signature for a symmetric matrix? A hat, the transpose should be equal, so A hat transpose, is it equal to A hat? That's the question. So what is A hat defined as? L transpose AL. So I need to take its transpose. So transpose will just flip it all around, right? What will I get? L transpose A. That's straightforward. Okay. Right. If we can use the SVD to get a low rank approximation of A, remember the problem was that A had a bad condition number. So the student is asking if we use SVD to get a low rank approximation of A, it would also decrease the condition number. Can we use this low rank approximation in conjugate gradient method and get similar offset as effect as preconditioning? What do you think? SVD itself is what complexity? Order n cube, right? So if I am going to do a SVD to get a low rank approximation, I have already done the hard work, right? So as it is, it's not a good idea. However, there are some inexpensive techniques to get approximate, like you don't have to do the entire SVD, you could just get a few of the eigenvectors. So those again fall into the domain of linear algebra. You could use those techniques to get some approximation, right, which has a better condition number. Remember, we don't need something very, very exact. We just need some trick to improve the condition number so that our iterations speed up. So again, this falls in the domain of numerical linear algebra, which we are not going to go into detail. So Omkar's question is, what is the order of the difference between A and KK transpose, right, the incomplete Cholesky and the actual matrix? Can the magnitude of this difference be limited while maintaining the sparseness of K and the low computational cost? That's one question. A related question is, why incomplete Cholesky gives a sparse matrix only? And okay, so and another is, how do you compute the incomplete Cholesky decomposition, right? So these are all questions of numerical linear algebra. We are not going to do it in this course. The algorithm itself of incomplete Cholesky is quite straightforward. You Wikipedia it, you get a pseudocode. If you wanted to just implement it, you can. Okay, understanding would require reading a text in numerical linear algebra. This would not be done in a first course on linear algebra. This is numerical linear algebra. I think the math department has a course for it. Calling a matrix with bad condition number means you have calculated it, which in turn requires calculating A inverse. So what the student is saying, that the definition of the condition number is so how will I know the condition number unless I calculate A inverse, and therefore it seems like a bad idea. So remember, this is the definition of condition number, right? This is not in practice how you will calculate the condition number numerically. Again, it's a whole branch of numerical linear algebra to calculate what is this condition number without obviously expending order n cube. So no one's going to do this. This is as good as writing the solution when I write A equal to B, B equal to, what am I writing? X equal to A inverse B. This is the symbolic way of writing the solution. It doesn't mean I've actually calculated A inverse and then multiplied by B, right? That was class 12, but that's not how it's done. So this is just a formula. How to implement it is again fairly rich field in its own, okay. And remember, in what we did last class, we are never calculating, we had this incomplete Cholesky decomposition, right? We never calculated any inverse anywhere. We worked that out in detail, right? So that cost has been saved. Okay. Any other questions not discussed just now? Okay. So what we have done so far is we have completed the basic version of conjugate direction method. We saw how that gave conjugate gradient method, and then we gave a practical version of the conjugate gradient method, which is the preconditioned conjugate gradient. So this completes the description of conjugate gradient method, and now you could implement it decently. The next version that we're going to look at is the nonlinear conjugate gradient method. Okay? Question? Okay. So in your usual conjugate gradient method, usual CG, the cost function which we had written was a quadratic form, right? And we had written it as half of x transpose AX minus B transpose X, right? And we said this is the same as effectively solving AX equal to B. Why? Because grad fx equal to 0 was AX minus B. Okay. Now, having experienced the success of the usual CG method, the question that comes is, can phi be a general convex function? What do I mean by a general convex function? Means not just a quadratic form. There can be other functions which are convex but not quadratic forms. Remember the definition of convexity, right? We had drawn the graph and function value lies below. So this is one question. The other question is, it's related to this, can phi be a non-linear function? So this is, if you pose this question, the answer turns out to be a yes. But we have to obviously make some modifications for this to work. And these modifications are sort of more or less common sense, right? So what changes will we have to make? Can you think of, looking at the recipe of the usual CG, what would be the first or one of the things that changes? So what was the special property of the quadratic form that got used in the CG method? Positive definite, but no, now we no longer have positive definite. Okay, so positive definite is out. Some general function has come to us. How did we calculate step length in CG? It was exact step length, right? Can I do that here? I cannot do that here. Why? Because, I can do it, but it's going to be very expensive. So I have to give up exact line search and replace it by inexact line search, right? So step length exact line search not possible. So I have to give up something. Okay. The other small modification that I will have to make is, remember the expression for the residual. The residual was what? Ax minus b. Now there is no a and b, right? So what should I, if you were in charge of affairs, what would you replace the residual expression by? Grad fx. Right? So that's the second change that you need to do. Replace Rx equal, sorry, not equal to, by grad f of x. Okay. Alright, now let us say I make these two small changes. Now let's try to just list out the modified CG method. Okay, so let's see, do I have all the nuts and bolts in place for this? Let's see, right? So check the new procedure. Step 1 was what? In our usual CG, I have picked a, let's say I've picked x naught. That's randomly chosen. What would be the next step? Grad fx, okay, I can calculate grad fx naught. Okay, obviously I have access to calculating function and gradient value. So I calculate grad fx. How does this help me? This gives me r0, which is related to minus p0, right? So I've got my initial direction to go into. Okay. What do I do with this next? I've got the direction in which I have to go to. What do I need to go to x1? Alpha 0, right? So to, therefore, I need alpha 0. How am I going to get this? Step 1, I mean the first thing over here, right? I don't have an analytical expression for alpha, no problem. I replace it by a module of inexact line search. I can do that, right? So, inexact line search, right? That took me to x1, okay? Now I need to update my p, right? So, what was my original expression for pk plus 1? We said that it is related to the residual, or in this case now the gradient, plus some linear coefficient times the previous search direction. Now if you look at the expression for beta k plus 1, if I just replace the residual by grad, what will I get? So is my recipe, modified recipe now complete? Do I have everything in place? We are not getting into the proof that this is going to work or not, but will the recipe as it is work? I've got a way to calculate my alpha, I've got an expression for beta, which gives me my new conjugate direction. I can now rinse and repeat and go through the iterations. Would you agree? Right? So yeah, I mean, we were all several decades late to the party. So two people by the name of Fletcher and Reeves made this small modification, and the first non-linear CG version is named after them, right? So this is basically what I've outlined over here is Fletcher Reeves, we're going to call this NLCG. So it's very simple. I mean, it looks very simple because minimum modifications to the usual linear CG have been given, right? What is missing over here? We have no idea that this is going to work. So what is the big difference now between linear CG and non-linear CG that we have glossed over? What was critical in the case of linear CG? Positive definite, which was used for doing what? For making the conjugate directions. The p's were conjugate with respect to a. Now there is no a. So the meaning of conjugacy itself is no longer valid because I have a non-linear function in general, right? So these are the things that we need to look at a little bit more. Okay, so let's see. But is everyone clear on the minimum modifications? Right? I just replace residual by grad, and the rest of the procedure goes along with the inexact line search. Okay. So the problem is A conjugacy is gone. If conjugacy is gone, what can I do? How can I still save the story? The hint is think of gradient descent. In gradient descent, I did not have A conjugacy, I had something else. What was that something else? Orthogonal, right? Orthogonal to, not orthogonal. That was a consequence, but what is the more primary property? What did I ask for the search direction? It should be a legitimate descent direction, right? In gradient descent was a special case where it was exactly in the negative gradient, but in general, remember that cosine theta, as long as I am in making a acute angle with the negative gradient, I am guaranteed that to first order that my function value is going to decrease, and we call that a legitimate descent direction. So since A conjugacy is gone, we at least should have something. Right. So, that something is fallback on ensuring that P is a legitimate descent direction. Okay. So, Pk needs to be okay. So, just to remind you graphically, if this was my grad f, okay, then right, my theta k had what range from minus pi by 2 to pi by 2. That was the meaning of legitimate descent direction, just as a refresher. Okay. Now let's get into a little bit more of the details. So I'm just going to rewrite the update equation for the P. Am I satisfying this at the start of iterations with P0? I am, trivially, because I'm starting with P0 equal to minus R0, which is minus grad of x. So I'm satisfying it at the starting, which is great. But how do I know that as my iterations go, my P's continue to be legitimate descent directions, right? I have to ensure that, otherwise the whole thing will fall apart. So let's look at the update equation, which was what? Let's write it for Pk. So Pk was minus grad Fk plus beta k Pk minus 1. Okay. So if I want to test legitimate descent direction, what do? Dot product with grad fx, right? So let's left multiply by grad f transpose. Okay. So what is the first term on the right hand side? Minus norm squared of grad fk. Is this good news or bad news? It's good news. Why? Because this term is always going to be negative, right? So that's already good. And then I have beta k grad fk transpose pk minus 1. So this is great. On the other hand, this term could potentially be problematic. Why? Because if this exceeds norm grad f k squared, then what will happen? Pk will no longer be a descent direction. So, so looking at this term is really one of the tricky parts of nonlinear CG. Okay. So, to study it, first we will study it in a more theoretical way, then we will see practically what is to be done about it. So, let us say, just for sake of argument, say that I did exact line search somehow. Okay. So, let us say that here I am at xk minus 1 and this is my pk minus 1 and I arrive at xk. Okay. So, I am choosing xk minus 1 because I want to evaluate this term over here. There is a pk minus 1, right? Pk minus 1 is involved in the journey from xk minus 1 to xk. That is why I am writing this over here, right? So, these are the 2 points over here. Okay. So, if I were standing over here at xk minus 1, what is the function that I am looking at? Like I want to find out the alpha that gets me to xk. So if you remember, we had written it as a function of one variable. This was f of xk minus 1 plus alpha pk minus 1, and we were hunting for the best alpha, right? And whatever best alpha I get, what will I call that? I will call that alpha k minus 1. Right? Once I find it, I will call it alpha k minus 1, whether by exact or inexact line search. Let's now, for sake of argument, assume that I did exact line search. Now, what was the defining feature of an exact line search? D phi by d alpha should be what? 0. Right? So if I did exact line search, it would imply that d phi by d alpha should be equal to 0. By multivariate chain rule, what happens to the right hand side? Grad this transpose pk minus 1. Now this whole expression over here, what is the short form notation for this? Is this grad fk or grad fk minus 1 or nothing? Right, this is nothing but grad fk minus 1. Oh, sorry, this is grad fk, right? Because this expression over here is nothing but xk. Right? So this is grad fk transpose pk minus 1. And this should be equal to 0. Does this look familiar? Right? It's the exact same character on the right hand side of this. So simple argument, right? It assumes that I did exact line search. If I did exact line search, this term is 0. If this term is 0, then the expression on the top over here, grad fk transpose pk, became equal to minus norm grad fk squared, right? So that's great news. This term is always guaranteed to be negative, right? So if I were to say this in plain English, how would you write this observation in plain English? Question? Correct, I agree with you. I'm starting with the ideal case and then I'll make it non-ideal. In the ideal case, if I were doing exact line search, what is the consequence over here in plain English? It is a descent direction, but it's saying that if I start with a legitimate descent direction, the next pk is also a legitimate descent direction. So if I do exact line search and I start with a legitimate descent direction, all along the way I keep getting descent directions. Right? So that's great. That is giving me a clear way forward of implementing a nonlinear CG. Make sure I do exact line search, no matter how expensive it is, and pick a descent direction to start with, then every step will be this. Right? So let's just note that down. If I do exact line search and start with DD, which is a descent direction, implies all P's are DD. Why? Because they always make a negative, acute angle with the grad f minus grad f direction. Now, of course, as was pointed out, this is, if I am doing nonlinear CG and my function is expensive to evaluate, obviously I don't have the luxury of exact line search, right? So in practical cases, we can say that exact line search is not possible. Okay. Now, thankfully for us, there is a lot of analysis that has been done on this problem. So there is, I'm just going to state the theorem statement that helps us, okay? And as you can probably guess, it has something to do with the Wolff conditions. So if you do the Wolff conditions in a certain way, even though you don't do exact line search, you continue to have legitimate descent direction. So I'll state it here without proof, okay? So the fix is impose the strong Wolff conditions, with the following. C1 came from which Wolff condition? Sufficient decrease. C2 came from curvature condition. And here it's not just curvature condition, it's the strong Wolff condition. So remember we put the mod sign, right? So that was our C2. Earlier we had said when we first learned the Wolff conditions, C1 less than C2 less than 1. Here it has become a little bit more conservative, it has been made half. Okay, so this is without proof being stated. Okay. If you impose this, then all directions are very, very simple to implement condition, right? So that's why it gets implemented a lot in nonlinear optimization, right? So that's all we need to do. We give up our exact line search, we replace it by an inexact line search, make sure that the Wolff conditions are followed in this way, and I go back to this recipe over here, the Fletcher Reeves recipe over here, start with minus grad f, walk through the steps, and everything works out. Now, it's hard to, so this is one of the first versions of nonlinear CG. As you can imagine, when people would have implemented it, there were some issues that came up. Okay, so there are actually several versions, or you can say cousins of nonlinear CG which are there. I'm going to cover only one more. There are several more, but I'll cover the two main ones. This is the first one that you should know because it's the closest related to the linear CG. Okay. Now, what happens is when you look at this situation over here, the geometry of pk and minus grad of k. Legitimate descent direction means that this angle should be acute, right? Now, it is in many problems observed. So, I am giving you an observation, I am not proving it or anything, an empirical observation, that if you take this Fletcher Reeves method, after several iterations, what starts happening is that this angle theta k tends to pi by 2. Okay. Now, if it tends to pi by 2, what's going to happen? I kind of get stuck because I'm not proceeding in a descent direction. So, I'm kind of going along the contours of the cost function, right? And so, progress is stopped. So, let's just make a note of this. Often, theta k tends to pi by 2. It is still strictly less than pi by 2. So, it is a legitimate descent direction. But if that angle becomes really, really small, then I cannot progress. Okay? So, knowing that this nonlinear CG has sort of been cobbled together like almost like a cooking recipe, if you were in charge of fixing it, how would you fix it? It doesn't require any fancy math, so let me keep this over here. So, you can in fact show that if this descent direction, if theta k is tending to pi by 2, it can be shown that pk plus 1 and pk, they become almost the same. So, then what can we do? Decrease beta k, that's a great idea. How much should I decrease it to? There you go, that's all there is to it, right. So, supposing pk plus 1 is turning out to be equal to pk, almost equal to pk. What is I am not bound to this beta k parameter. I have defined it from looking at my linear CG. Nothing is holding me to it. So, what should I do? If he said, let's reduce beta k, let's take it all the way. If I drive it down to 0, what happens to my pk plus 1? It becomes minus grad fk plus 1, which is a great descent direction, right. So, that's actually what is done. So, set beta k equal to 0, rather this is called a reset, because it is resetting the descent direction. Okay. Again, we were late on the scene, so the guys who figured this out got their name to it. Polak-Ribiere. Can never get the I's and the E's correct. Okay. So what this method is doing, it's basically just a small variation of the Fletcher Reeves CG, and I keep monitoring theta k or cos theta k. As this theta k tends to pi by 2, I do a reset, and then the same recipe follows along. Okay. Now, because there is the expression for beta k, in this the only loose kind of thing is how do you define beta k, right? This has been written down by observing the linear CG. So there are people who have come up with different and more efficient expressions for beta k, and so that has given rise to a full family of nonlinear CG methods. Okay. The theoretical analysis of it is quite difficult, so people will do it heuristically. You try several different versions and you see it will work well on a nonlinear, the Polak-Ribiere may work well on one problem, Fletcher Reeves will work well on another problem. So it's hard to say anything very definitive about it, but these are the options available. If you use a numerical linear algebra library, they'll give you headers for all of these different versions for you to try out, okay, for that reason. Okay, so this is, in a nutshell, your nonlinear CG method. Okay, it's the only theoretical thing of importance over here which we didn't derive was the fact that this one over here. As long as I maintain this Wolf condition with C2 less than half, everything goes through and you have a thing, right. So if you have a nonlinear method to optimize, here is a very, very simple recipe that you could do. What is the other simple recipe that we have? Gradient descent. Gradient descent. Right.
So how will you decide when to set beta k equal to 0?
Again, it's a heuristic. So theta k is never going to become pi by 2, right? So it's going to become, so you can put a threshold. If theta k minus pi, absolute value of theta k minus pi by 2 falls below a certain threshold, you reset.
So you will use beta k from the Fletcher Reeves equation.
Correct.
But when the angle reaches,
you reset it. For one iteration, you set it to 0, and then you let it. Then you use the rest of the formulas.
if it is always 0, then it's simply CG.
If you do always 0, this is, so this reset is only one iteration, not for all iterations. If you do it for all iterations, it becomes gradient descent.
Okay, once we make it 0, let's say we get a set of another pk. For that, will we again use the beta k or like?
Then it's a reset. I set it to 0. It's like starting from P0. Now I follow the rest of the recipe. So it's like something's getting back, you reset it. Then something's getting back, you keep resetting. Right? So for one iteration only. So only one iteration. Okay. So it will be good if some of you can try to just write a simple code for this. Take a nonlinear function. In fact, there are benchmark nonlinear functions available if you Google for it. Right? Functions which are known to be very notorious nonlinear functions. So people benchmark their nonlinear optimization methods against these known things. And then when I publish my results, you can see which method is doing better. If I come up with a new method, I can say, look, hey, against this benchmark, my method works well. So I'll post a link to this library of ugly functions that you can try out your various ideas on. Okay. All right. Any thoughts or questions on this? It's fairly descriptive. There's not much derivation involved over here, so it is what it is.